conferences, and I went like almost every semester, and it's really great to be back. So there are sort of two parts to this talk. There's geometric Manin's conjecture and non-free curves, and I went back and forth on exactly which one to put first, but I landed on Manin's conjecture. So I'm going to start and tell you about a conjecture in number theory, and then I'm going to continue and tell you about some like geometry of curves things that we can prove that I claim have bearing on the conjecture in number theory. But let's start with some number theory. So let's let K be a number field. And let's let X a smooth projective variety over K. And let's let X be Fano, which means that negative Kx is ample. And so from a number theory, when you're trying to study rational points on varieties, there are sort of two basic cases. There's when Kx is ample-ish, and then you expect very few rational points, and you're trying to prove there are very few. Or when negative Kx is ample, and then you expect there to be lots of rational points, and you're trying to prove that there are lots of rational points in a very precise way. And that's what I'm going to talk about today. So the question is, how many rational points in a general piece of X? Oops. And so if you're trying to picture it, you've got your variety X. And we don't care about weird stuff that happens in some special subvariety. We care about, like, if you just take a little general slice, we're saying how many rational curves are in that general slice. Now, the answer is infinitely many. So this is not, as I wrote it, a well-posed question. But what we're going to try and do with Manin's conjecture is get down to something that makes sense and that we can try and prove. In order to do that, I need to talk about the height of points, which I don't want to get into. There's a lot more to say here, but I'm just going to say the most basic version. But if you have a point in projective space, right, we're assuming that X is projective, and we're using negative Kx to embed it into projective space. So you just take some embedding to be able to talk about a height. And then the height is roughly the size of the coordinates of P. And so the technical definition is it's the product over all valuations of the maximum of the valuations of the coordinates for each possible valuation. And so like this is the definition, but what you should think of is this is just the size of the coordinates of P. Right, so for any fixed height, there are only finitely many points with height less than that, like with small coordinates. And so you're saying as you let the size of the coordinates grow, we're interested in how many points are in X. And so, that is Manin's conjecture. So for a suitable finite extension of K, and if we take, and for some set of accumulating points, which there are conditions on this S that I will have to get into later. Then the number of points in X that are not these accumulating points, like the points coming from subvarieties and like from special things, but like sort of the points that come from general parts of X of height up to P. This is about some constant times h to the a log h to the b minus 1. So I'll tell you what a and b are in a second, but first I want to let you know what the general form of the conjecture is. We're saying the number of points in X is roughly, it grows like of bounded height, it grows like some explicit function of the height. So this is really precise information about the height, about the point, rational points. Yeah?
What's this? Where does the finite extension come in?
Well, so like if you,
K prime or?
yeah, I should have said this is, yeah. Maybe I should write K prime. I'm saying like let K be some appropriate finite extension. For example, if you take a Brouwer-Severi variety, there are no rational points, and that's like clearly bad. So you have to take some extension to like make sense of it. But it's saying like for the right extension. All right, then let's talk about what A and B are. So B, there's a technical definition that I won't get into, but you should think of it roughly as the Picard rank of X. And then A is this thing called the Fujita invariant, and it's something you define relative to the embedding into projective space. So if you take your X and embed it into projective space with the very ample line bundle L, then the A invariant is you take the inf among all real numbers T such that Kx plus TL is effective. Right, so the idea Kx is a negative thing, right? L is ample, so L is positive. And you're saying how negative is Kx with respect to L? How many L's do you need to add on to Kx to get something effective? Let's do a quick example, like a quick and easy example of this. So if X is Pn, then the canonical bundle of Pn is negative n minus 1 times the hyperplane class. And so the A value of Pn with respect to the hyperplane class, well, how many H's do you need to add on before you get something effective? N plus 1 of them. So this is n plus 1. And so you can see, and the Picard rank of Pn is 1, so you can see that this term is going to go away. And so what this is saying is in projective space, if you bound the heights of the coordinates, the number of rational points with those heights is like h to the n plus 1. Which makes sense, right? You've got like h choices for each coordinate. Like you imagine over z and you say like you're only allowed integer coordinates up to like 79, then the number that you expect is like 79 to the n plus 1. And so that's what Manin's conjecture is saying in this very simple case. Any questions about that? Like this is sort of.
If you were embedding by the anti-canonical.
I usually am embedding by the anti-canonical, and so I mean as you change your H.
In that case, A is 1.
Yeah, and so when you embed by the, but it's not as nice. We don't have as nice understanding of that. Like we don't have as nice a geometric picture. Yeah, so if you embed by the anti-canonical, then you've scaled all the heights by some number, and this A captures it. Usually, what we do is we use the anti-canonical bundle, so A is 1. But then you don't have the same intuitive understanding of heights, so I didn't want to use that for the example. So now I need to talk about this accumulating set S. Manin's conjecture, it's been checked in a lot of cases, in several cases, and it seems like it's right. But there are also counterexamples if you don't allow this accumulating set. The idea of the accumulating set is that the counterexamples should all come from some sort of bad, like special geometry of X. They all come from like the same sort of place, and so you should throw out those types of points, and then just keep your good points that get you the right order of growth. But there's some ambiguity on how to define S, and so I want to talk about a couple principles. First, it must come from bounded data. Right, if you allow your set S to come, like if you allow like countably many components that like your S comes from, you could just like that's all the rational points. So you need like S comes from some special subvarieties or covers of X, and you need that set of varieties to be some bounded family. There need to be finitely many components to the family. Maybe they vary continuously, like maybe you have like a cover by elliptic curves or something, but the family of elliptic curves is bounded. It's often defined non-explicitly as a thin set. And a thin set is just the image of k points under a finite non-birational map. But if you like in the classic, it's just said as a thin set with no description of the thin set. That's a little bit a whack-a-mole conjecture, right? Anytime you find too many points on some X that you think might be a counterexample, you say, oh no, that just goes in the thin set. And it's like really hard to tell whether you're still proving your conjecture or you've just like made it complicated enough that you can't describe it. And so Akash and Brian and Sho have a framework for, they like describe what they think the thin set should be. They like put forward a proposal for a type of thin set, and they say if you assume Manin's conjecture, then everything works consistently. And so I can't go into all the details of it, but I'll at least tell you like one of the principles of this is that the thin set. So if you have a subvariety of your x where the Fujidian invariant is bigger than the Fujidian invariant of x, then you expect more, like if Manin's conjecture is true, you expect more rational points in that subvariety than you had on all of x. So definitely that has to be in the thin set. And even if you have a subvariety where the A invariant is like the same as the A invariant of x, that's a subvariety where you have almost the same number of points in this small subvariety as in your entire x. And so you expect that to also have too many rational points. So the thin set, or this accumulating set, it should probably come from the subvarieties with Fujidian invariant at least one. So it must contain the points from the subvarieties y and x of Fujidian invariant at least one. Bigger than 1. And you expect sort of the ones where it's equal to 1, you expect those to kind of be in the thin set too. And I should write down, so the paper where they develop this is Akash and then Lehmann and Tanimoto.
Are you saying nobody yet has definitively conjectured what S is, but we know it must at least contain these? Is that what
No. Akash and Brian and Sho do definitively conjecture what S should be.
And is it this set?
And yeah, it's the set of not quite. Yeah, it's a subtle. There are a lot of like sort of like overlapping similar. Like I'll put forward a different proposal for what it should be. That if you assume geometric Manin's conjecture, it is the same as the one that Akash and Brian and Sho use, but we can't prove that it's the same. Yeah. And so now, and that's the number theory conjecture. The number theory conjecture is hard. And I mean, this is really precise information about the rational points, and rational points are really hard to study. There's been a ton of important work on this, but like knowing it for like all Fano threefolds is like not close to what number theories currently do. Yeah?
I just want to ask, when you say non-birational, do you mean exactly what you said, or do you mean it's not sort of subjective?
Surjective is okay. Yeah, so I
also, this last point, y is assumed to be Fano also?
No, I mean y could be singular, and so then there's some resolution, and the resolution might not be Fano, but it's like sort of spiritually Fano. Like, yeah. Or I mean, no, y could be like you blew up at too many things to make it truly Fano. It's like like if you run the MMP on it, then it becomes Fano.
You mentioned like elliptic fibrations, could it be an elliptic curve?
Y, as I phrased it, it could be an elliptic curve, although that's not.
I'm just saying,
Yeah.
you know, the conjecture with the A and the B, I assume that only refers to Fanos, and then so if I know I have my Y, which is not a Fano.
Yeah, y is sort of spiritually Fano. Like when you talk about the Fujidian invariant being big, like that means ky plus tl. Like you need a lot of t's to make it effective. And so even like it might not be literally a Fano variety, but ky is like pretty negative in the sense that to make it effective, you need to add a lot of effective things. And so if you run the MMP on it, then you do get a Fano thing. So it's Fano in that sense, but it's not precisely a Fano. All right, so I remember a talk. I can't remember for certain if it's an AGNES talk, but it was a talk, and I remember Brendan Hassett's, he was talking about sections of del Pezzo fibrations, and he said, he like motivated it with a number theory conjecture and said, I'm not a number theorist, I'm an opportunistic algebraic geometer, and so I saw a problem where I think my knowledge of curves can help, and then he proceeded to dive in and describe how that works. And I say the same thing, I'm not a number theorist, I'm an opportunistic algebraic geometer, and so I wanted to talk about how I can use knowledge of curves to try and shed light on this conjecture. And so to do that,
Sorry to interrupt,
yeah.
but an opportunistic algebraic geometer might also prove something about curves over finite fields.
Yes.
So is this conjecture also for those global fields?
That's exactly where I'm going. Yeah. So how do you picture Q points? Right. So how should a geometer picture one? You have spec Z, spec Z, and you have you can take some neuron model, right? You take the equations that define your x, and then you like clear denominators and write them over the integers, and so you have some family x of varieties over the integers. And maybe you have to remove an open set. But for each prime p here in spec Z, you have a variety in PQ over a finite field, like a different finite field for each one. And if you have a Q point, that corresponds to, well, for this prime, you like reduce the coordinates mod this p. And for this prime, you reduce the coordinates mod this p. And for this prime, you reduce the coordinates mod this p. And so you have a section of this map from X to spec Z, right? The Q points are sections of a map from your neuron model to a one-dimensional base. And suddenly this looks more like something geometric, right? And so just as Jason was saying, you can also consider the space of sections of X over some curve, which corresponds to the case of when your base field is fq of a curve over a finite field. Right, and so how do we think about this? We have a curve over a finite field, and we've got a Fano fibration. It's a family of varieties, and the generic fiber is a Fano variety over the function over fq of b. Right, so we're studying the sections. This sec x over b, this is the space of sections of the map from x to b. And it's a family of curves. This is like this is the key transition. So now I'm interested in this number theory question, but I'm trying to study curves. And so this idea is very common in number theory. And the person in this case who did it, Batyrev, did some work, and he has some heuristics to explain like what does Manin's conjecture predict in this case.
Before Manin.
What?
That's where Manin's conjecture comes from.
Is from Batyrev's heuristics?
Yeah.
I stand corrected. I didn't know the history. Yeah. So let's understand what the story is. So if you assume Manin's conjecture, then you take x to b as a Fano fibration. And you take M in the space of sections, a component. Right, again, this is a family of curves on X, each of which is a section of the map from X to B. Right, I should draw what a section means. Right, you take for each point of B, you have one point in the variety up above. Right, so it's a curve in this X that maps isomorphically onto B under this projection. In this setting, if C is a section, then the height of C is the usual normalization you use is you let the height be q to the negative degree of C. And so if you assume Manin's conjecture, this implies that the number of sections of X over B, the space of sections is a variety defined over FQ, right? B is a curve over FQ, and so the sections are all you can talk about the FQ points. And so Manin's conjecture gives you a prediction for the number of these points of given height. Oh, and I went too low, didn't I? And so the Weil conjectures tell you, I think I'm better off going to this board. Right, the Weil conjectures, even if you don't know exactly what they are, they say if you know the number of points over FQ, they tell you important things about the geometry of your variety. And so they imply geometric Manin's conjecture. And depending on how much you know about the FQ points of your variety, you might know different layers of information about geometric Manin's conjecture. So there are 3 layers of things you might know. If you know the first order of growth of the number of points, then you might see that each component of the space of sections has the expected dimension. All right, this is if you knew the first order of growth, like just like leading term of the like coefficient exponent of the leading polynomial of growth. If you knew even more precisely the number of curves, then Manin's conjecture would tell you that the number of components of the space of sections with like some given cohomology class is equal to the size of the Brauer group. But I mean, so the Brauer groups aren't so important. The point is, it's some fixed number independent of the cohomology class for really large cohomology classes. And then if you knew, wait, and I said this is like this part is if you knew the leading term. And if you knew even more information, which often there is a couple of really important counterexamples where we do know more, but usually we don't, at least right now. Then the cohomology of components of the spaces of sections, they exhibit some stabilizing behavior.
So all of this is still out of finite extension of K?
In theory, I think actually for when you have a family of Fano varieties over a curve, then you actually like, you don't even need to extend. I think it works.
You don't know their no.
You don't know.
You don't know their sections even after you extend FQ. You don't know that.
All right, then yes, after some appropriate.
You don't know Fano manifolds are separately rational things.
Yeah. We should talk about this after. Yeah. So perhaps you need to make some extension of K, or perhaps there's some other. In characteristic P, it turns out to be actually really hard to prove geometric Manin's conjecture. However, the statements I just wrote down, which came from Manin's conjecture, and I stated them in characteristic P, but there's no characteristic P in any of these statements, right? These all make sense over C. And so if you're an opportunistic algebraic geometer, you've seen this really hard conjecture in number theory that people have spent a ton of effort on. And now you have a set of things you can check about curves over C. And I love curves over C. And so we should bring our algebraic geometry tools to bear on these questions.
In B, the left-hand side looks like it depends on beta, but is it saying this is in particular independent of this classification?
Yeah, exactly. This side is independent of beta. And so like this could be different for each beta, but the conjecture is saying it's not. It's like for large enough beta, it's always the same.
Wait, why do you say large enough?
Because for Manin's conjecture, you always throw away finitely many low degree points. This is the conjecture that I'm trying to like address in this talk. Yeah, it's the Brauer group. The idea is it's the difference between algebraic equivalence and numerical equivalence. And this is numerical equivalence, and like the number of components is like roughly algebraic equivalence. But I mean, even getting this to be some bounded number would be a big advance. So there's been a lot of prior work on Manin's conjecture, and I don't want to like eclipse that, but I have so much else to say, I can't do it justice. And so what I will do is I will mention just a couple of names of prior work, this is not at all exhaustive. This is just if you wanted to learn more about all the different types of things and get a flavor of the types of things that have been done on Manin's conjecture, then you know where to start searching. And so there's a paper of Gorodendijk. I might have switched the D and the N there. Mocourant and O, where they prove they're working with homogeneous varieties over a number field. And this is sort of generally, unless you're working over a number field, unless you have some very special variety, like a homogeneous variety, it's really, really hard to do. I mean, it was really, really hard for them to do this as well. But like, if you don't have some homogeneous structure, I don't think people have strong ideas. For just a general variety of like dimension 20, I don't think anyone would know where to start. Then for hypersurfaces in lots and lots of variables, there's been a lot of work using the circle method. And that's one of the like triumphs of this theory. And so I can't say there are a ton of people who have done this, but some of the big names are Browning, Salwin, and Visha. And Will Salwin will actually speak here later, although I don't think about Manin's conjecture. But they study high dimensional hypersurfaces over a number field or over FQ of B. And they're able to prove A, B, and some versions of C, actually, which is really striking. It's like very rare to be able to get versions of C.
But sorry to keep interrupting. That technique goes back to Swinner to Dyer, and that also, I think, was one of the motivations for Manin.
For Manin's conjecture, is that it worked for some high-dimensional hypersurfaces. I did not know that either, but thank you. Yeah. I mean, there's a long like history of study of Manin's conjecture. So for geometric Manin's conjecture, so this is over C now. If you take B equals P1 and you take your family of varieties X to be like the Fano fibration, you take it to be the trivial Fano fibration. And you take the dimension of X to be at most 3, then we roughly know the conjecture. We know A and B of the conjecture. And this is work of a lot of probably more people before us, but the last step was by by 2 of my students, one undergrad and one grad student, Andrew Burke and Eric Giovanelli. And it was built off of some work of Roya Beheshti, Brian Lehmann, myself, and Sho Tanimoto, and then also Testa. And proving A and B. For this talk, I want to make the case. So I have a theorem for this talk, and the theorem is roughly that we prove A only, but for any Fano fibration. So it's so we don't get this more precise versions from B and C, and you have to as was clear when I was waffling a little bit about the definition of accumulating set. You have to use our version of accumulating set, which is slightly different from previous versions. But if you do that, then I claim we prove A for all smooth Fano fibrations.
But so not just over P1 and not just constant P1.
Correct. And so now I'm going to start talking about curves and what exactly we show in this case. Any questions before I do that? This was the end of like the number theory half the talk, and now we're going to start talking about curves.
So can you just say more about C? I just didn't get that.
Yeah. So there are a bunch of components of like spaces of sections, and it's saying as you take the degree of these components to be high, you can take the like singular cohomology of each component, like the topological cohomology. And the conjecture is that there should be some limiting behavior, maybe in terms of like a loop space of X.
Yeah, that's the Cohen-Jones.
The Cohen-Jones-Siegel. Thank you. Yeah, it's conjecture. Yeah.
What happens to that set in this statement?
Yes. Oh, sorry. I should have. It's there all the time. Let's. I meant to say and forgot. You have to remove it, and you always have to remove it. So let's let sec star of X over B be the set of sections of X over B, not on an accumulating component. And I haven't told you precisely what I'm trying to argue that this should mean, but it's something about like subvarieties with higher A invariant or components coming from those subvarieties. And then all of these statements are about sex star. Yeah. Yeah, so you remove them in every case. Yeah, thank you. Any other questions? All right, so then just to like recap, so now our question has become, if we have a component of the space of sections, I mean, or even any component, because we need to identify which are the special ones. And then we want to know when does M have too large dimension. Right, so we want to study large components of the moduli space of curves. So anytime in algebraic, I mean, you can't do this in number theory, but anytime in algebraic geometry you have a component and you want to like bound its dimension, you should look at the tangent space. And if you can bound the dimension of the tangent space, then you've bounded the dimension of the component. So we should be studying the tangent space to the moduli space of curves. And there's a standard tool for doing this, right? You have some curve C in your variety X. And at each point, you want to know, like, so the tangent space is how can you wiggle the curve in X. So it's a first order deformation. You want to say, like, for each point, which ways can you budget so that it moves off of C? Right, and the way to measure that is it's exactly sections of the normal bundle of C in X. And so what we want to do is we want to understand the curves where the sections of the normal bundle is the expected or non-expected dimension. And the components that are bad, the ones that have to be thrown out when we take section star, are the ones where this is always too big. And so let's make that definition. Let's let, we say a curve C is free. So free if it's good. If the normal bundle is globally generated, and H1 of the normal bundle is 0. Right, so there, Riemann-Roch tells you if you know that H1 is 0, it tells you that H0 has the expected dimension. So these are the curves that are good. And anytime we have a component of curves that contains even a single free curve, then we know it has the expected dimension. And so we know it's good from our perspective. And so the ones we want to throw out are the ones that are not this. They're called non-free curves. And so our goal is to understand the components of, are the components M of the space of sections consisting only of non-free curves. And so I want to start a theorem that tells the classification. And then I want to, as I like state the conditions in the theorem, I want to give examples to show why these have to be in the theorem. And so let's let X over B be a Fano fibration. And let's let M be a component of the space of sections. And we're gonna start saying which things about M let it be non-free. Yeah.
So are you saying that there couldn't be components that have proper subvarieties with bad sections?
Right.
Or because you're only caring about the dimension, you just want to throw away whole components where the generic section is bad?
Right. The only components that screw us up for A are where every curve is bad, right? And it's very typical that you'll have some component that's mostly good, like it has the right dimension, and it just happens to be singular in some little locus. That's fine. Like the fact that some of the curves in the component are non-free, no problem. Like great, Manin's conjecture holds for those. The ones that are really bad are where every single curve in the component is non-free, and those are the ones where we're trying to control.
But still, even in those components, I mean, the exceptional sets should still contain those small pieces if you're going to think the whole conjecture.
No, that's not important. Like from a Manin's conjecture point counting thing, these like the small singular locus, those don't screw up the count. Like the way to screw up the count with the Weil conjectures is to have just tons and tons of points, like as if you had a component of too large a dimension. Having a couple points that like don't have the right deformation property, no problem from the number theory perspective. Thank you for the question.
These aren't S. They're not subvarieties of X. They're subvarieties of spaces of sections.
Right. Yeah, S is like the S is like rational points or like spaces of section, like point. Yeah. Any other questions? Yeah. So let's see some ways to construct components of all non-free curves. We're going to go. So I want to write the theorem there, but I've made it over to this board. I think the theorem actually needs to go over there. Yeah. Right.
You're going to have non-free curves on every single component. You're not going to find a bounded subvariety that explains the non-free curves because you're going to have non-free. I mean, every component is going to have non-free curves.
Right. Yeah. So there are going to be lots of these that are non-free, and I have to what I'm trying to do is I'm just trying to throw out the ones that form their own component. I'm allowing the ones that are like subvarieties of good components. I have to work very hard, and I have to argue very hard that the ones we're throwing away come from bounded data in some way that I'll make precise at the end of the talk. So we're doing some examples of components of non-free curves. Example 0. Let's suppose the dimension is too small. So let's suppose we've got f from B to P2, and we're taking x is equal to x. We're taking just the product case, right? And so let's try that again. We're taking the product case. X is the product of some curve B with x. Let's let B be a smooth degree 5 Platen curve. And so B is a smooth curve contained in P2 of degree 5. We're letting X be B cross P2. Sorry. Let's try that again. I will do example 0 in just a second. It will be that, but I wanted to set up a setting for all the examples. For the examples, it's easier to think about the product case. So let's for all of the examples, let's let X be X cross B. And let's let f from B to X cross B be a section. Right? And this section, it corresponds to just a map from f from B to X. Right? The map from B to B is always the identity. So we just want to understand the map from B to X. And that'll tell us the section. And then in this setting, the normal bundle is just the restricted tangent bundle of X. Like you take a map from B to X, and you can just pull back the tangent bundle. And so we want to understand the restricted tangent bundle. And then so for our example 0, we're going to let f from B to P2 be just the inclusion of a smooth plane curve of degree 5. Of high degree d. And so here the genus is going to be really big. It's like d squared. And the degree of f upper star tx is going to be 3d. And so you can see for large d, there's no way that h1 of tx can be 0. Right? Just high genus curves, you need pretty big degree to show that there's no h1. And so anytime you have a low degree curve relative to its genus, then it's very easy to have components of non-free curves. And this is one example. And it turns out d at least 5 is enough. So that is one counterexample. So we need to assume that the degree of the curves is high, which we certainly do. So now let me start the theorem. Let's let x over b be a Fano fibration. And let's let M be a component of sections, of the space of sections. And we can assume that they have high degree, because we know definitely if they have low degree, then they will not be free. Then we're in one of these three main cases. And so let's keep going with our examples. Oh, sorry. Any questions about the setup and what we're trying to do? We're saying, suppose you have a non-free component of curves. Suppose the non-free component has the curves in that component all have high degree. Then we're trying to classify what it looks like geometrically. I'm trying to say that it comes from bounded data in the variety. Yeah.
So the degree is with respect to what?
So when I say degree here, I mean the anti-canonical degree, like negative kx over b, like the sort of degree, intersection with negative kx over b. Any other questions? Let's do another example. So non-free curve. Let's suppose our subvariety, let's suppose the curves don't move very much. Like suppose they're stuck in some subvariety. So let's let x be the blow up at p of p3. Right? What does this look like? We have our p3. And then we blew up some point, and so we replaced it with a p2, which we call E. It's the exceptional divisor. And we're taking the family of curves inside E, and it turns out that those will form a component. Right, so B is contained in E. And so here we have, anytime you have an inclusion of subvarieties, you have a map from the tangent space of E to the tangent space of X restricted to E. And this maps to the normal bundle of E and X. And because this is a blow-up, we know that this will be OE of -1. Right? The exceptional divisor of a blow-up, it's sort of negatively embedded in the projective space. And so in this case, you can see it's going to be O of -1. We are interested in understanding whether this has H1. Let's do it. Let's restrict to our curve. So we have F upper star TE goes to F upper star TX goes to F upper star O -1. And we see this is a negative degree bundle, so it'll have H1 usually. Right? If the genus is bigger than 0, then this will definitely have H1. And even if it's a rational curve of high degree, it'll have H1. This has H1. So when we take the long exact sequence in cohomology, we see that this has to also have H1. So the fact that this has H1 implies that Tx has H1. So these non-dominant families of curves will typically have H1. They will typically be non-free. I mean, in fact, you can see that the normal bundle will not be globally generated for these. So then either X is not dominant. Lie in some closed subvariety V contained in but not equal to X. That's certainly a case we have to rule out. Any questions about that one? Let's do another one. Let's talk about another way you can have non-dominant, non-free families of curves. For this family, we're going to say the curves look like they have high degree, but all the high degree comes from one direction. And so here we're going to let X be P2 cross P2. And we're going to let F from B to X be a map from a smooth degree 5 plane curve of by degree 5 comma D, where B is a smooth degree 5 plane curve. Right, so we took a smooth degree 5 plane curve that had H1, that was non-free in just the P2. Now we're taking a map to P2 cross P2, and we're letting the degree be really big, but only in one factor. It's like low in the first factor relative to the genus, and it's high in the second factor. So the total degree is high, but only in one direction. These are also bad. Right, if you take F upper star Tx, then this is just X is just the product, so it's just the direct sum of the restricted tangent bundles on each of the map to each factor. And the first factor, it has low degree, and so this has H1. So F upper star Tx has H1 for this entire component of curves. So we have this definitely is the case we have to rule out as well. And so how do I say it more generally? So there exists some rational map phi from X to Y, maps of B varieties. And this is a fibration such that curves of M have small image in the space of sections of Y over B. Right, just like in this example, we took these curves of by degree 5D. They had it was a huge dimensional component, but when we took the image in this P2, it was a small dimensional family. It's just like the space of degree 5 curves, whatever that dimension is. Any questions about that one?
So these are like the matter of Jinko example, the second one?
Yes, because it comes from like a fibration, like an elliptic fibration, right? Yes, these are like that. And then the third example is if the fibers are disconnected. And so let's let X in P4 be a smooth cubic threefold. These have been extremely well studied. And their families of lines have also been extremely well studied by many, many different people. And so there's a two-dimensional family of lines. And it's known that there are 6 through a general point. Right, you take your two-dimensional family, you can show that they sweep out all of your cubic threefold X, and you say for a general point of X, how many of them are there through that point? It turns out there are 6. So 1, 2, 3, 4, 5, 6. Now let's construct our family of curves. Let's let M be the set of maps from B to X that are just multiple covers of a line. And it turns out this will form a component. And let's assume that the genus of B is at least 1 for this example. Let's think about And so let's see that these are non-free first. So we have, if we take Tx and we restrict it to our line L, like I said, these are really well studied, and it's well known that it's just O of 2 plus O plus O. Basically, you can see the line has anti-canonical degree 2, so it has to have total degree 2. It sweeps out, so it has to be globally generated, and it has to admit a map from TP1, so that's why you have to have the O of 2. Now let's take this and restrict it to our G. And so we have FF star of O2, which has high degree, and then it's just O, the pullback of O is just O again. And for a high genus curve, these will have H1. And so we can see the restricted tangent bundle has H1. I claim that the reason this is able to happen is because it factors through a finite cover. Akash and Brian call these A covers. Right, so you have the universal family of lines, and right, this is the space of lines. This is a point on the space, like pairs line point, and they map to X, and it's a 6-to-1 map, right, because there are 6 lines through the general point. And our M cross B factors through this cover, right? The curves factor through the space of lines, so we get 6 so the M cross B to X, that map factors through a finite cover. And the claim is that finite cover is what allows us to see that that allows the curves to be non-free. And so case 3 is that the generic fiber of MB cross X, M cross B X to X cross, sorry, M cross B to X is reducible. And the statement is that in each case, the curves of M lie in proper subvarieties Z of X with larger A invariant. So the A invariant of Z over the generic point is, with respect to the canonical bundle, is 1. Right? It's these ones that we sort of suspected earlier are the type that you have to remove. And so this theorem, what it does, let's talk about what it does and doesn't do. It classifies the non-free components of curves, the ones that are bad, that violate A of Manin's conjecture. It says these are the ways that you can have an accumulating component. However, this does not yet show that they come from bounded data. And so I need to tell you some theorem that says, hey, all of these accumulating curves come from some bounded set of data.
Should that be greater than that?
Yes. Greater than or equal to. Like equal to 1 is also bad. Any questions about this classification theorem you could have been interested in without knowing about Manin's conjecture, right? It's just saying non-free curves are hard to understand. Here's like a classification of how they happen.
So sorry, are you saying 3 is a special case of 1?
No. 3 is a special. Yeah. The M cross B to X, they dominate. However, and so I'm not saying there's a single Z that works for all the curves. I'm saying there's some family of Z's such that each curve here comes from that Z. Yeah, thanks. That's a subtle point. I'm glad someone asked. Right? It's like in the P2 cross P2 example, we have this family of P2s. And like the fibers of the projection map are like a family of P2s. All right, then let me state the last theorem that's a version of saying, hey, this comes from bounded data. And so let's let X to B be a Fano fibration. So first, for case 1, we need to be able to say, this is saying individually for each M, there is some closed subset. we need to be able to say that the same closed subset works for all the infinitely many m's that you could have. And that's indeed the case. Such that any component of sections that's non-dominant lies in R. Right, so it's not saying that there are finitely many components of M, but it's saying that all the components of M that don't dominate come from finitely many subvarieties of X. And then part 2 is sort of case 2 and 3 together. And it's saying there is a bounded family of varieties let's call them ys. They're parameterized by some bounded set curly s. And they all map to x. And these are like the smaller subvarieties with larger A invariant that contain all these curves. The dimension of y is less than the dimension of x. So this is saying they're accumulating in some sense, right? They come from smaller subvarieties that have the same A invariant as the whole total space. Any non-free component of high degree that sweep out X has a general curve lift to some ys. Right, and it's the same sort of picture as before. It's not that it's not that you have a component, each curve is in some ys, is in like the same ys, but for your component of curves, you have some family of ys's that contribute all of the curves in this component. And then C is that the A invariant of these ys's is large. Yep. So the A invariant is at least 1. And moreover, these are adjoint rigid. So it means the Ataka dimension. When you take the effective class that's on the boundary, then and take sections of it, you don't get very many. And so to summarize one time before I end, what we're saying is we said geometric Manin's conjecture, to like the most basic prediction you can make from it, is that if you have non-free curves, they come from some bounded set of data relating maybe to the A invariant. Like they come from an accumulating set in a way that you have to make precise. And so what did we prove? We said, well, we're trying to classify these components of non-free curves. And we said we have a geometric classification of them. And we can make our geometric classification so that they come from bounded data. So we have an understanding of an accumulating set that where if you use that understanding, we know geometric Manin's conjecture. Thank you.
Are there questions?
Yeah.
Can you say something about what goes into the Brook index?
Yes. So there are a lot of different ingredients. The main new one that hadn't been used on Manin's conjecture before is the Grauert-Mulich theorem, right? So knowing that a curve is free, that's sort of equivalent to something about the slopes of the Harder-Narasimhan pieces of the tangent bundle, right? You take your tangent bundle, you restrict it. If all the factors have really high slope, then you'll be free. So we're looking at the restricted tangent bundle. We're trying to say it has high slope. And so you start with your tangent bundle on your x, and there's like a notion of slope with respect to a curve class. And so if the slope is high with respect to the curve class, the Grauert-Mulich theorem is a restriction theorem that says, hey, the Harder-Narasimhan filtration of the restriction is roughly the same as the Harder-Narasimhan filtration of the original thing. If you start with something that's not stable, then there's no hope that like the restriction to the curve would be stable. But then you can use a theorem of Campana-Pound to construct a fibration like this in 2. And so these 3 cases, like if you have a dominant family of curves, that rules out case 1. If the tangent bundle originally is unstable, then that's like case 2. And and then the Grauert-Mulich theorem needs an irreducible fibrous hypothesis, which is case 3. And there are examples of like case 3 not like breaking it. And so to get this classification, you use the Grauert-Mulich theorem about stability. Then to get the boundedness statement, you need techniques from the MMP, including like Burkhar's BAB and stuff about boundedness of subvarieties of A invariant. It's not unrelated to techniques that Akash used in the paper, but you have there's new stuff too. Thank you.
Oh, there is. There.
So to get your classification, did you somehow think about Manin's conjecture and the exceptional loci to give you intuition, or go back the other way now that you understand kind of these exceptional components? Does that shed any light on the original arithmetic Manin conjecture?
I think so. I mean, I think if you're studying Manin's conjecture from the number theory perspective, I think this makes a case that these are the things you should be looking at from Manin's, like instead of this thin set, which was like a little, I mean, in some sense, this is what like Akash and Brian and Show were already doing, is they're saying, don't have it be just like some nebulous thin set that's not defined. Have the thin set be coming from these A covers, these finite covers that have like particular properties. These should be the accumulating components. And so this is in the same vein. It says like if you're looking for, like if you're trying to find some sort of thin set or some sort of bound, like you should be looking for a bounded family of subvarieties of A invariant equal to 1. And so if you have a potential counterexample to Manin's conjecture and your counterexample points do not come from a bounded family of subvarieties of A invariant 1, that means it probably should, like Manin's conjecture is wrong. Like our understanding is incomplete. It doesn't work. But if you are trying to argue something in the accumulating set, this is what you should be looking for, is these subvarieties of A invariant 1. Yeah, I mean, I think that in some sense that's one of the motivations for this project, is to like understand what should be true in number theory, because we can state theorems in the geometric context.
Are there any further questions? Well, if not, then let's thank Eric again.